I know it when I see it. The true measure of quality. Any user will tell you if they had a good experience or not. In-flight connectivity is a little difficult to measure. Typically, the focus is on Service Level Agreement, or SLA, and that relates to another thing we hear about, which is Quality of Service, or QoS. QoS really focuses on radio technology that connects the airplane to the ground. A radio channel can be set aside for different users, groups of users. Those are network slices. Within a particular network slice, you can differentiate service between users. That's called traffic shaping. Intertwined with all of that is cybersecurity. I'm Peter Lemmy. You can find me on the web at www.satcom.guru, on Twitter at satcom_guru. Well, I need an analogy for service level agreement, or SLA, and I thought it would be fun to think about finding a parking spot at a business. I'm sure you've all gone to a grocery store or hardware store and you expect to find a spot, hopefully near the door so you don't have to carry your stuff too far. If you show up and there is no spot, well, that can be frustrating, and you might end up going to a different grocery store with more parking. So I'm going to call that SLA, providing a parking spot. So I'll show you in this example, there's a single spot available and a little blue car arrives. That spot's open. The car pulls in. Service level agreement has been satisfied. We have provided a parking spot. The question is, how many parking spots do you need to provide? That's capacity. What happens if it's hard to find a parking spot? We'll call that contention. What if you can't find a parking spot at all and you just leave? We'll call that congestion. So let's say you arrive and the one parking spot is occupied. There's somebody in it. What are you going to do? You're going to leave. This is an example of congestion. The SLA was not met. Well, the business owner is not going to be happy about that. So what are they going to do? They're going to add capacity. Maybe they're going to add a second spot. So now you can see there are two spots, but one of them is filled. The other one is available, so you arrive and, well, you just pull into the second spot. This is an example of contention. The SLA was met. You found a parking spot. You had to choose between the two. Maybe this one's a bit further out, but you got your spot. Well, even with two spots, you could still arrive and both spots are full. What's going to happen? Well, you're going to leave. Congestion. SLA was not met. So perhaps in a progressive situation like this, the business owner may respond more aggressively. Maybe they're going to put 6 spots in now instead of just the 2. Obviously, there's plenty of spots available when you show up and just 2 are occupied. It's an example of contention. The SLA was met. Again, it might not be the best spot, but you found a spot. Well, the business owner is paying for 6 spots, and 3 of them are sitting there open. This is unused or excess capacity. Let's take a look at a bigger example. Here we've got a parking lot with a whole bunch of parking spots. In this example, 2 of the spots are occupied and a car arrives. Obviously, it's not going to be a problem to find a parking spot. Well, what if those 2 cars in the lot were using more than their allocated spot? For example, what if they were overlapping into an adjacent spot, or even 3 or 4 spots? Their usage is way above what the SLA guarantees, but it really doesn't matter. You can pull in, you can find a spot. In light usage conditions, contention really isn't that big of a deal. You really don't have to worry too much about how the users themselves are behaving. However, there's a lot of excess capacity here, and I don't think anybody wants to run their network this way. So this might be a little more pertinent example. Here you can see that most of the parking spots are full, but not all of them. It's still not too difficult to find a parking spot. This is an example of contention. The SLA is met, and it's a bit more efficient network because there are fewer open spots. What if you arrived and there's only 1 spot available? It might take a while to find that spot. There was a spot available, so you can argue there SLA was met, but it took a while to find it. There was substantial contention. Some people might have left feeling the SLA was not met. What if you arrive and there's no spot available at all? It might take a while to figure that out, which could lead to quite a bit of frustration. Not only did you not serve the customer, there was congestion and their SLA wasn't met, but you also probably frustrated them. They may not even come back to the store because of this experience. Well, that example is a bit extreme, so consider this situation. 4 cars are leaving, and 4 cars now are waiting for those 4 spots. And 4 more cars have arrived. So there's a total of 8 cars that are in circulation did not have spots when they arrived. Once the 4 cars pull out and the cars waiting pull in, the remaining 4 cars circulate until they find 4 more cars ready to pull out. Now all 8 cars have parked. Nobody left, there was no congestion, and we handled 8 more cars than our capacity would suggest. However, there was some delay, and this gets back to an SLA that promises to provide a parking spot, but now needs to require the parking spot to be available within a certain amount of time upon arriving. So what kind of parking spot should we have? We've talked about how many spots we need, but does every spot serve everybody's needs? What if we have a different kind of user involved? Well, in this case, I'm going to show it as an ambulance, a little red ambulance. Could be a wheelchair van or something like that, but it needs access and proximity for loading a stretcher or wheelchair. It's important to have space available if a wheelchair van arrives and somebody needs it. You want to make sure they can park. What happens if an ambulance arrives at a parking lot and there's no space available for them? So what I'm going to talk about is network slicing, right? Where we have more than one user involved. In the black cars, those are just regular cars, and in the red we have the ambulance or the wheelchair van. And we're going to treat each of them as part of a different network slice. So in this case, there is no capacity, no parking spot available for the ambulance. Their slice is congested, and they're going to leave. So that's congestion for the network slice serving the ambulance. However, all the other cars appear to be parked. Their SLA is met. It gets more complicated with network slices because you have to have an SLA for the ambulance, which in this case it was congested, while a different SLA for the typical car, which in this case was contested. So what's the answer to this? So you could set aside some of your capacity to serve these other users. So in this example, 2 of the parking spots are set aside for an ambulance or wheelchair user. I'm showing those with the little red icons. All of the other spots are available to anybody arriving. An ambulance actually could park in any of the spots, but only the ambulance can park in the 2 spots that are marked with the red icons. This is an example of network slicing by priority. With an available spot, when the ambulance comes in, there was contention, but there was nobody else to contend with for these particular spots. It appears all the network slices are being served. So how about this case? Another user arrives and there's no available spot for them, even though there are 2 spots sitting there vacant. They can't use them because they're reserved for the ambulance. They're going to leave. So this is a case of congestion. The SLA was not met for the little blue car. Well, it would be interesting if we could make use of those 2 spots while they don't need to be used by an ambulance or wheelchair user. So here I'm showing in a different color users that are parked in the wheelchair spots just because they happen to be able to give way or give up their spot. They can use it, but they'll lose it if a higher priority user arrives. This is a way of achieving SLA by using unused capacity from a higher priority network slice. So it's not perfect. If an ambulance arrives, then that user is going to have to leave. In this case, their SLA no longer is met due to congestion, but the ambulance did arrive and got their spot. Their SLA was met. The ambulance or wheelchair user could use any spot, but what if you had a big RV or were towing a trailer? These just don't fit in a single spot. They need more spots. They don't fit in the network slice that's set aside for the other users. If they show up and don't see any place for them to park, then they're going to leave. Their SLA is not met. So we'll call them a heavy user. You might think of them as a video streamer or something like that, but in our example, they just don't fit in a single spot. They need 2 adjacent spots or more to fit in. One way to solve this problem would be to set aside a few spots for RV-only parking, pull-through parking, things like that. These can be set aside on the outer fringes of the parking lot. Reserving capacity for the heavy users is a different kind of network slice, setting aside more capacity for a single user. In the case with the ambulance, it's the same capacity, you just have priority to the other users. If the RV shows up, they can just pull right on in. There's still contention, but the SLA was met, and everybody's happy. What if you arrive and you find that a bunch of network of RVs have showed up and hogged all the spaces? The heavy users are starting to squeeze your experience. You're having to work pretty hard to find a parking spot. This is an example of a user doing something, using more space than they should, and that doesn't seem fair. That leads us to what we call traffic shaping. So here a car shows up and one spot appears to be open. But a parked car has managed to take 2 spots. The other spot is the only one available. So that's a problem. This is a user taking more than their fair share, more than they deserve. You need something to fix that. So in this case, we have a little tow truck that goes over there and repositions the car to put it back into its space. That's what we're going to call traffic shaping, or putting users back inside their lanes. Now the other spot opens up, and everyone's SLA is met. Well, now let's talk about in-flight connectivity. The following figures use nomenclature that was first described by the Seamless Air Alliance. We'll start with a user device. Let's say that's a laptop, a cell phone, or a tablet. It could connect to an onboard wireless network, a Wi-Fi network, or a wireless LAN or WLAN. On board the aircraft, there's some form of AAA. That would be authentication, authorization, and accounting. The backhaul is a radio network that connects the airplane to the ground. Half of that is on the airplane on the left side, if you will. The backhaul connects to the resident hotspot provider, or the HSP, and they provide internet access. If it was a cell phone, it would connect to the onboard radio access node, in this case an eNode B. An onboard core function provides some form of AAA, and the mobile network operator, or the MNO, sits on the ground providing internet access. The interconnections between onboard components, such as access points, head-end servers, the portal, backhaul, in-flight entertainment, are preferably VLANs, or virtual LANs. VLAN IDs segment the traffic corresponding in part to network slices. A backhaul radio has its own way of slicing traffic. It might have channels set aside for system essential signaling or other kinds of services. It's also mixing traffic with other aircraft. The radio channel management blends with the VLAN ID segmentation to provide network slicing. A service level agreement may exist with regards to the backhaul radio, and for some end-to-end services. Quality of service is indicated in some manner. VLAN IDs are discussed in AWC Project Paper 688 within the Network Infrastructure and Security Subcommittee, or NIS. These are also described in ARINC 791 Part 2, which is proposed to follow these concepts which I'm presenting. VLAN IDs are segmented by domains as described in ARINC 664. There are 4 domains, but 3 of interest includes a public or passenger-facing domain, a private domain for in-flight connectivity and in-flight entertainment, and a secure domain for avionics, just not relating to safety of the aircraft. Differentiated Services Code Point is one method for marking in the IP header. Class of Service, or COS, is one method for marking in VLAN, is another way of doing marking in the Ethernet frame header. Those are both connectionless methods. QoS Class Indicator, QCI, is another measure of per-hop behavior. The order of preference for marking VLAN is VLAN Class of Service, then DSCP, and finally connected QoS, or what physical or port did you connect in. The marking is shown as a sequence of bits. This provides for 4 layers of quality of service: expedited forwarding, assured forwarding, and then best effort. The idea is to divide the users on board by service levels. So, for example, one slice could cater to those that have not purchased any IFC plan. Another slice could be set aside for those purchasing a messaging product, perhaps best effort. Other slices could be used for those with browsing or streaming products, such as assured forwarding. So any domain can apply 4 or more different slices. The network slices may get into bit rates or latency. Quality of service and service level agreement are related to channel capacity and information rate. However, none of these are directly related or indicative of users' experience. Quality of experience is an elusive measure. Users don't use the internet the same way. One person could be browsing, another person might be doing email, another person's on Twitter, another person's watching something on YouTube. They've all purchased similar products, but they're trying to use them in very different ways. How do you measure quality of experience? SLA sets the quality of service for the network slice, but not the quality of experience. All of the users are on the same network slice. Is one user getting a good experience and another one getting a bad experience? Quality of experience relies on user-based measurements. That involves some form of packet inspection, and that gets to traffic shaping. The most basic form of managing users is by restricting their data rate. Sandvine is a well-known provider of network optimization. Their portfolio of services are a good indicator of what's available, and they target specific aspects to provide a robust solution. Each of these services or tools is managing quality of experience for some or all of the users. Now, for example, they have fair usage and congestion, which is priority by application or application type, by source or destination, by network type. Video streaming management, which is effectively managing the video bit rate. Heavy user management, I call this the penalty box. TCP optimization, they come up with a term called good put, defined as payload without retransmissions. Satellite communications in particular suffer with TCP because of high latency. And then traffic steering or diversion, and they say diverting traffic for value-added services often requires steering at the application level, which has become increasingly difficult to do with the continual rise of encryption. Sandvine's active network intelligence classification engine uses machine learning to ensure accurate traffic classification in spite of encrypted DNS and TLS 1.3. This active logic function defines the maximum achievable efficiency for traffic redirection far beyond imprecise port-based approaches, reducing the number of router ports, load balancing devices, and value-added services elements needed. So you can see traffic steering in particular is quite a complex undertaking. So there we see the traffic shaping coming in. Placement of network optimization features favors a central location on the border of internet access. However, some features could be best served on board the aircraft. Regardless of the technology or application, the user has a perspective. I know it when I see it. Passenger interaction is another measure of satisfaction. Did the session result in typical usage? How active was the session? Is this a repeat user? Is there any trend? Portal interaction can be monitored directly for difficulties or queries that suggest frustration or a problem. Direct user interaction by refund or adjustment, a survey, message, or voice offers a definitive measure. And that becomes our user experience measures. Cybersecurity is never far away from any network discussion. ARINC 848 has been released and provides a foundation for this discussion. Cybersecurity and quality of service have a tendency of interfering with each other. Cybersecurity methods can blind quality of service. These methods for marking QoS described here are designed to work with cybersecurity features. So the idea is to make sure cybersecurity and quality of service complement each other. The architecture builds around an air-ground radio. On board the aircraft is a remote terminal offering connectivity for passenger services. The backhaul function involves a wireless connection and utilizes proprietary and confidential methods for managing each radio channel, considering quality of service and service level agreement. Every radio has unique attributes and features. They're not the same. A communication service provider, or CSP, extends the backhaul connection to the internet. The CSP was referred to as the resident HSP or resident MNO earlier. AAA functions exist within the backhaul to manage remote terminals and within the CSP to manage users. This commercial off-the-shelf or COTS layer includes backhaul and the CSP. Best practices for public internet is provided as a part of the service. Service providers compete on features in cybersecurity as a differentiating feature. The subnetwork layer sits above the COTS layer, and this is where 848 lives. The Media Independent Secure Offboard Network, or MISON, M-I-S-O-N, is a is a virtual private network, or VPN. For example, IPsec. The MISON connects an onboard LAN with an enterprise LAN. An enterprise could be an airline or a third-party service provider or content provider. Is the methodology. VPNs use QoS markings, such as COS or DSCP, that are evident. This allows for differentiating between traffic types. Here you can see the tunnels formed, and they're managed collectively at different priorities, and then you can see each enterprise can have one or more terminations depending on how many different network slices are supported. Each one of them is a MISON tunnel. An application channel sits on top of all of this. This is where the information is exchanged. This is the third tier in defense in depth. The application itself has to have a mechanism to ensure that the source of data or information it's communicating with is authentic, and that the information that's being provided has not been corrupted, or at least to a level of assurance that's acceptable. So the MISON VPNs are added, and we have the firewall at the COTS level representing specific cybersecurity features. The onboard segmentation by VLAN ID and by MISON or other aspects of network security. MISON channels are established by the onboard MISON client and subject to certificate-based authentication. The MISON client drops any traffic not associated with an active MISON channel. Keep in mind that only non-passenger traffic is managed using MISON. The passenger on board is provided best practiced public internet. Methods promoted by the Seamless Airlines provide for a WPA3 enterprise level security for the user device attaching to the onboard Wi-Fi.